voltage equation and equivalent circuit of synchronous machine.
Which part is you will not include it now? This
Yeah, and others.
Which part, sir?
Only for 1 to 3, 1 to 6.
Is include only exam?
1 to 6. Yeah, I will give you some examples of the exam tomorrow. Okay.
So only, sir, 1 to 6, yeah?
Yeah, 1 to 6. So here. The other falls
is not.
Not included, and there's no in the 50.
Yes, yes. So you don't need to learn.
Yeah, no need to learn. So the important is the equivalent circuit. Let's see this. This is a three-phase synchronous machine. Has two poles, and it's the cross-sectional sketches of a three-phase machine. The three-phase armature, the three-phase armature, A prime, B prime, and C prime, is the three-phase state windings. So it is simple to represent the distributed windings. They just producing sinusoidal MF and flux density waves in the air gap. And the field F and F prime is the rotor winding. Also, the rotor winding represents distributed winding, just like this figure. It's distributed. There are many windings on the rotor, but for the simple purpose, we just use F and F prime to represent it. We know that this equation, lambda equals to Li. L is the inductance of a coil. I is the current. So this equation we have learned it in chapter 1. So the lambda is flux linkage. Inductance and the current in the coil. So this equation is the best meant to understand the equivalent circuit of the synchronous machine. If you don't know the meaning of this equation, you can find it in chapter 1 in the textbook. Before we learn the equivalent circuit, we have know the mutual inductance. Yeah. This is two coils, coil 1 and coil 2. There's two coils. It can be represented by this figure. This circuit, the L1 is the inductance of the coil 1, and L2 is the inductance of the coil 2, and the resistor R1 or R2 for coil 2.
This is the part.
Yeah. We know if the two coils are near one by one, the distance is short between them, there will be the mutual inductance between them. Also, we call it magnetical coupled coils because the distance is short. So the voltages induced in one circuit is related to another circuit. See here. The mutual inductance can be M1 2 or 1 to 2 or 2 to 1. The two inductance are equal. So we called the L1, L2 is the self-inductance, and the M between them is the mutual inductance. The voltages induced in one circuit is related to the time varying current in the other circuit. So they are related. We see this figure. The inductance of between the two coils, inductance is influenced by the distance of the if the distance is short distance, if influence is strong. If large distance, the influence can be omitted. But we know this is a synchronous machine, three-phase synchronous machine. It's the stator coil, and this is the rotor coil. The distance between these coils are very short, because they are in a small cabinet. The distance is short, so there will be mutual inductance between A to B, B to C, C to A, and rotor to stator, rotor to A, and rotor to B, rotor to C. So the mutual inductance between all these coils. So there are complicated relationships between them. And we say use this equation. The flux leakage is a function of inductance and current. Use this equation. We can give the complicated equations of a synchronous machine. We can say that there are four flux leakages, lambda A, B, C, and F. F is for the rotor. It's also for the field rotor. And we say the L, A, B, C, and F is the mutual inductance between the A to A is example, and A to B to C, A to F of the building. Similarly, we can do the lambda B, lambda C, and lambda X, and the next. So these equations are complicated, and the inductance also here. Maybe in some textbooks it used this is M. Just we have learned in the mutual inductance M. But many in textbooks they also they are used A, B. So A, B, AC are mutual inductance, and but AA, FF, BB, CC, they are self-inductance. So this is equations of the circuit of the synchronous machine, and we should know we should calculate the inductance. Let's see. First we see the self-inductance LFF. LFF here is the rotor self-inductance. The LFF is equal to LFF0 plus LFL. So the LFL is the leakage flux component. We know every machine or motor there's leakage flux. Just as we have studied in induction motor and DC motor, there are also leakage flux. But here the leakage flux we used LFL to represent it, and the LF0 is the fundamental component because we have omitted the harmonics for 3 or 5. We have just omitted. So we just see the fundamental component LFF0. So this is LFF. We have learned one. And also the self-inductance L, AA, BB, CC. For a three-phase synchronous machine, generally the three inductance are equal. Also, they can be obtained by the LAA0. Also, it's the fundamental, and LAL is the leakage flux. This is similar to the LFF. So we have the four inductance. There are self-inductance. So let's see others, and the mutual inductance, just as LAB, LBA, BA here, and here. And also the SC, BC. There are six inductance. Generally, they are also the same. But it is a function. It's function of the electric angle. Function of angle. So I use cosine of 120 degrees. So it can be simplified as the minus 0.5 L I0. I0 is this one. I0 is the self-inductance. So the mutual inductance is 1/2 of the self-inductance. So this inductance also can be calculated by this equation. So and we have also the mutual inductance between the stator and rotor. Here is AF or FA, and also the BF, FB, CF, and FC. This mutual inductance are the functions of the electrical angle omega E, omega M, omega T. Yeah. Also it used and theta M. So it uses these three equations. There are 120 degrees between them. This case minus is plus. So use this equation. We can calculate the mutual inductances between the stator and the rotor. So now we can calculate every parameter in these equations. So substituting equations for the self-inductance and mutual inductance into the expression of the flux linkages, lambda equals to Li. Yeah. We can get this matrix equation here. It's just a lambda NBC test. So it's the parameters here. We see this one. This one in here is L A, and we know LAA is equal to LAA0 plus LAL. So here the LAA is replaced by this item. So it's equal, and also for the other parameters, they are presented by this matrix equation. On the balanced three-phase system, the fast summer of the ABC phase current, the sum of them is 0 because it's a balanced system. So we can know the IA equals minus IB minus IC because it's a balanced system. So for the lambda A is here, lambda A is lambda is LA0 plus multiplied by LC, and this one multiplied IF. It's the matrix calculation. We get this equation and replace the IF with minus IB and IC. We can get the last of the final equation. The final equation here. Let's see. The final equation is this one. We can simplify it. Simplified. There's L0 here and also L0 here. So these two items can be replaced by 3 over 2. L0 and this one L here. And plus this item. So this variable we define it as the synchronous inductance. You see here. It can be designated by LS equals to 3 over 2 L0 plus LS. Just use LS to replace this one and this not bearing here. And finally, we get the simplified equation. For flux leakage or fluidity. For this equation, it's easy to calculate. The variables. Easy to calculate everywhere. Calculate the IF. So this equation is very important. To calculate the characteristic of the synchronous machine. And it's also the effective inductance seen by phase on the steady state balance condition. So this equation is only for the steady state condition. But for us, the steady is enough. We can calculate this steady state equations is enough. We don't need to calculate the dynamic state. So use this equation, this important equation, the LS, the synchronous inductance, LS, this equation. We can get the equivalent circuit here, the equivalent circuit of a synchronous machine, The terminal voltage VS, it's just similar to the equivalent circuit of the DC motor. It's simple to the inductance in induction motor. Yeah, the induction motor. For induction motor, the equivalent circuit is complicated, but for synchronous machine, the equivalent circuit is simple, just as a DC motor.
That is for rotor, yeah?
Yeah.
For rotor.
The rotor and stator. This is a stator voltage. Yeah, stator voltage.
And the RA is the rotor resistance.
Yeah, for stator.
Hysteresis.
Yeah, for stator. Stator. It have included the rotor in them. It's the last. It's the final. It's the final circuit. Final circuit.
The EAF is the
Yes,
rotor.
is the we can think it is the bank EMF. It's the for the stator, but it's influenced by the rotor. It's influenced by the rotor, but it is in the stator. For synchronous machine, we use the stator circuit. It's enough. The influence is included in the EAF. We see here the bank EMF, EM is this the last. So EAF is equal to the DLAF IF dt. So we can see this. Although it is for the stator circuit, but the EMF is related to the inductance between the stator and the rotor. Yeah, EMF is related with the rotor and stator. So we can think this circuit represents the whole machine. We use the terminal voltage. The terminal voltage equals to the voltage drop on the stator resistance and the voltage drop on the synchronous inductance of LS. LS also here is XS, and omega XS equals to omega multiplied by LS. So it's the voltage drop, and the bank EMF. So the three items, and the sum of them is voltage, is the terminal voltage for the stator. This here is for phase A, and also similarly we can calculate the phase B, phase C, phase 3. You can see here this equation, the bank EMF, the RMS value can be calculated with this equation. That's the omega E is the frequency of the current and the LAF mutual inductance between the stator and the rotor, and the field current. If there's an example for you, that will give you these parameters for IF, for LAF. That will give you these variables. And also use to calculate the EF. The progress of the EF is these two equations, and also it can be represented by the complex form next one is just use it as a vector. It's a vector. Also the vector form for the terminal voltage is this equation. It is from the this equation, this terminal equation. From this equation, we can get the vector form. So here, if it is for complex and the vector form, there will be the JXS here. It should be noted that this figure is known as the motor reference. We know if it is if the machine is the motor, the current flow from terminal to the inner to the machine. So this one is for the motor reference, and we also can get the generator. We can get the generator reference form here, and the current flow out from the machine.
Just double integration.
So for the generator, the equations are different.
Yes.
Minus because the EAF is larger than the VA because it is generator. But for the motor, it's opposite. The VA is larger than the EAF. So, but the two equations both are okay. Both can be used to calculate these variables. Both can be used. If it is a generator, if the machine is a real generator, but you use the motor equation to calculate it, you can also calculate only the current. The sign of the current will be different. For example, is the generator, but if you use this equation to calculate, you will get minus current. Just the sign is different. This the two operating motor. Just the power direction of the power is different. Yes, and this is the conclusion. This is the conclusion of these equations. We can calculate the terminal voltage, and synchronous inductance. Also, reactance is okay. XX reactance, and for the two modes for motor or generator, the equations are different. Just the sign is different. So this is the equivalent circuit for the synchronous machine. Also, this figure, this figure is different from this one. We see here XSRN. We see here there's two inductance, but it's equivalent. this figure is an alternative form of the equivalent circuit. Also, it's the equivalent circuit, but just the inductance is divided into two inductance. So here we see Ls is of the X L X back X L back. So the sum of the X back and the XL is XS synchronous inductance. Just one inductance divided into two inductance, but they are the same. So it is an alternative form for the equivalent circuit. The XL is we know is leakage reactance, and the X back is the effective magnetizing reactance of the armature winding. So both for the two forms of the equivalent circuit, they are okay. According to different variables, you can use different circuit equivalent circuit to calculate them. And let's see the parameters. The XS in unit parameter. Some typical value of the synchronous machines. One for the smaller machine, and another for larger machine. If it's a larger machine, the power is large. For the smaller machine, just the power maybe 100 kilowatt, maybe several hundred watt for the smaller one. So the values is different. For the smaller one, the value is small. 0.5 to 0.3. But this just the typical value. Different machines will be different values. So let's have a simple conclusion of the equivalent circuit of a synchronous machine. You know, the field is supplied by DC voltage, DC output, DC supply to generate flux, and the three phases are distributed with 120 degrees, maybe delta or maybe star, maybe delta connections, different connections. The relationship between the current and the voltage will be different. And this one, we know the EMF. If for a motor, we will call it back EMF. For the generator, we just call it EMF. Is okay. Also, yes, the EF here EAF,
Very smaller.
EAF, EAF. Here is locked. Okay, this is conclusions of the synchronous machine. Okay, let's take a break. Well, we just studied the example on the textbook. Example 5.1. Yeah. For this chapter, we only need to learn the 5.1 and 5.2. Only two examples, and others we do not need to learn it. Only for 5.1 and 5.2. These two examples for this chapter. How to study and practice for the simple one. For example, 5.1 it is 60 frequency 60 hertz, three phase, and give us the terminal voltage, the VT, terminal voltage, but it is line to line. We have to transfer it to the phase voltage. This is a line voltage, and give us the power factor. It can be used to calculate the power, and give us the field current. The field current, the IF field current. So and also give us the inductance, synchronous inductance, 1.68, and this is the synchronous inductance. So it's for the equivalent circuit. We have just started. We should know the equivalent circuit and use these variables to calculate and others. For example, for A, to calculate the EAF. Okay? No electricity. Okay, no problem. Can other rooms? No electricity? Just wait several minutes.
Yes.
If it can't recover, I will contact tomorrow. Just wait several minutes.
2 minutes.